Hello everyone, my name is Mengchun Xie. I'm teaching in National Institute of Technology, Wakayama College, Japan. The title of this presentation is Optimization of Fuzzy Regression Transfer Learning using Genetic Algorithm for Cross-Domain Mapping. The plan of the presentation is as follows. Data science focus on the process and the systems included in extracting knowledge from vast amounts of data. Many machine learning methods assume the training data are collected from the similar feature space of distribution as that for the target domain. When the data distribution changes, the most statistical model requires the collection of the new trained data and the complete reconstruction of the model. However, these tasks are costly and sometimes impossible. Transfer learning, a machine learning method, addresses this issue by leveraging knowledge from models built in the source domain, where extensive data can be collected, and applying this knowledge to construct a model for the target domain. Translearning that offers the percentage of the high precision learning with minimal data and short training time. Secondly, transfer learning is applied to tasks such as classification of product reviews, spam emails, and web documents, and the estimation of Wi-Fi location. Numerous methods has been proposed, particularly of the text and image in classification. However, research on transfer learning for regression problem remained limited. Transfer learning is often combined with deep neural networks. However, domains with insufficient information can introduce uncertainty in productions. Fuzzy system capable of efficiently handling uncertainty have given the attention in such solution. Traditional regression transfer learning based on the Tagaki-Sugano fuzzy theory is effective only when the target domain has extremely limited training data. This indicated a highly restricted domain environment, making application to real data sets challenges. Moreover, only particular swarm optimization and differential evolution methods have been used for optimization mapping for input space modification. In this study, first, we verify the relationship between learning data in different domains using regression transfer learning method based on the Tagaki-Sugano fuzzy theory for domains with incomplete knowledge. Then, two methods, one based on the genetic algorithm and one based on D combined with an GA are proposed for optimizing mapping for input space modification. We apply this method to some real data sets and assess their effectiveness through evolution experiments. Transfer learning. Transfer learning is machine learning approach distinct from conventional machine learning, where training and testing are typically deducted within the same task. In transfer learning, the knowledge gained from a given task is utilized for a new task. In other words, transfer learning effective and efficiently addressed the data scarcity problem by reusing data and learn outcome from the related problem. In transfer learning, the source domain means where knowledge was transferred from, and the target domain, that means where knowledge is transferred to, are defined. The applicability of transfer learning depends on the strength of the relationship between source and target domain. Fuzzy regression transfer learning combined the Tagaki-Sugano fuzzy regression model and transfer learning. The fuzzy regression transfer learning will uplearning the fuzzy regression model construct based on the Tagaki-Sugano fuzzy theory to the target domain. It's necessary to modify the input space. In the other words, the space of the target domain is modified to adaptate to the source domain M using mapping phi. In order to make the target model M dash better, it's necessary to optimize the mapping phi. That means parameter alpha, beta, and W. Genetic algorithm is optimization algorithm inspired by natural selection and genetics. It belongs to the broad category of evolutionary algorithm and have been widely used to find approximate solution to optimization and search problem. GA is based on the principles of evolution and including selection, crossover, and mutation. In this study, we apply the GA to optimize the parameter of the mapping mapping phi. This follow of the genetic algorithm as follows. Initialization, crossover, mutation, evaluate the fitness solution, and selection. The presentation of invaders in the GA used a matrix whose size is determined by the number of attributed and the number of nodes. This is the representation of an invader parameter alpha is shown in this figure. Similar representation as use beta and W. Here, since we use real volume GA, each element in the matrix is random real number within a specified range. The fitness function uses the mean square error like this. equation. DE is application-based optimization algorithm, like force and evolution algorithm. In this study, we proposed a mapping optimization method that combined DE and GA, denoted as DEGA. Initially, optimization is conducted using DE. Then, further optimization is conducted by applying the GA to the solution set opted from DE. In this approach, the initial optimization used DE is performed to enhance the fitness of the initial individual for the real volume GA. It is expected that combined DE with GA will improve the predictions and reduce the reduction accuracy and reduce the computation time. In this study, we proposed 5 patterns for model M- in the target domain, where domain is transferred from the constructed model in the source domain. For example, M-T means model built with only target date. M-DEGA means phi and M optimization use DEGA method. The evolution metric used in the validation experiments on the real data set is the root mean square error. In addition, the state deviation of the production error defined in this occurrence. Validation experiments were conducted using the proposed phi method on real dataset. The phi model were applied to various tasks for real datasets. The proposed method was evaluated in terms of prediction accuracy and computation time. Cross validation was also performed. The experiment's conditions are shown in this table. In this experiment, the Boston housing dataset, an open dataset for regression problems, was utilized. For the transfer learning process, the input space was constructed using 2 attributes from this data set. Names room, that means a variety number of rooms in each neighborhood, and distance, that means distance from each neighbors to 5 environment center in Boston. The target variable was the median housing price in each neighbor. For the trans-learning task instance with attribute text below, 600 were considered as source data and other with text equal to or above 600 were considered as target data. 3 datasets with 30, 60, and 90 instances respectively. The input for the 2 domains is shown in the figure. The 2 domains have different data distribution. This table shows the results of 5 fold crossing validation for each trial, including the RMSE, mean, and D for various target data set, and the ratio of the average computation time. As shown in the table, MGA and MDGA often have smaller error than those for the other models. In this experiment, we used an open dataset related to debates for regression analyzed. The input space was considered using 3 attributes, names BMI, BP, and GLU. The target variable was the progression of debates after 1 year. Here, instances with range below 60 were used as source data, and those with ages equal to or above 60 were used target data. The input space for the 2 domains is shown in the figure. In construct to experiment 1, the 2 domains have similar data distribution. Table shows result of the 5-fold cross validation for each trial. As shown in the table, depending the data sublet, there are cases where MGA and MDGA have similar error than those for other model. However, on average, regardless of number of instances in the target dataset, MS has the best prediction accuracy in all cases. The last experiment, a dataset related a cancer in centers rates by country in the United States was utilized. The input space was constructed using 2 attributes, names IR and income. The target variable was the per capita cancer mortality rate for each country. Instance with a probability rate of less than 30% was used as source domain, and those with a probability rate equal or to about 30% was used as target date. The 2 domains have different data distribution. This table shows the results. There are cases where DEGA has smaller error than those for the other model. Discussion. The results for the 3 experiments confirmed that fuzzy regression transfer learning is effective for real data sets. However, in experiment 2, for which input space distribution of source and target domain overlapped, the modification of the input space adversely affected the learning process. In addition, due to the large variability in input data in a real data set, the method performed well even with large numbers of instances in the target date. On the other hand, for target data set with 30 instances, learning was insufficient. This is observation suggests that depend on the condition, negative transfer through mapping may occur. In this study, we applied fuzzy regression learning to regression problems in domains with incompleted knowledge. First, for the target task, we found the impactive of the retail of data between the source and target domain was negligible, but the distribution of data between the two domains has a significant effect. Incorporating of GA for optimization the mapping for input space modification improved production accuracy and reduced computation time. The proposed transfer learning method can only be applied when the domain dimension and attribution of the input space are the same. Feature challenge is as follows. Thank you for your attention.